expand, and as you can see, these are the direction of the normal vectors on a side, and that's on the other sides going down. So you have some of them going outward and the others of the opposite direction, dramatically or suddenly. As I told you once more, if you walk around the Morris strip with a tiny arrow perpendicular to the surface on a normal, after one loop, the arrow points in the opposite direction. The surface flips orientation, as I told you, suddenly from being upward to the inverse of this direction directly. This is also a comparison between the orientable surfaces and non-orientable surfaces with respect to normal vector. This exists globally and continuously, as you can see. If this is the surface, so it already exists, but it can't be defined globally. Has two sides, upper and lower, or the top and the bottom. Only one side locally appears to have two, but globally doesn't have. Okay, surface integrals well defined using the normal vector, not well defined without special treatment. You will have to assign some part in order to determine the normal vector. In physical examples as sphere, outward, inward normals, Morris strips flip the normals as you go around. This is why we did go through this part, in order to determine the normal vector, which will play a magic rule with us in trying to flip from surface integration into contour integration, or from surface integration to treble integration, as we will see. Okay, now for the orientable surfaces, and as I told you, these are the parts from our slides. Two-sided surfaces said to be orientable, with only one side is said to be non-orientable. The normal vector for the orientable, this is the n positive, that's the n negative. The non-orientable surfaces, you will have them both together linked in one part or one strand. Okay, flow of a vector field or the flux. The flux or a flow of a vector field. The flow of a vector field F direction, or the vector field across a regular surface sigma oriented by the normal vector n. Now I know why we told this. We are talking about the orientable surfaces. So we had to know that there is orientable and non-orientable surfaces. This is because of the existence of the normal vectors. It's really very simple. All I have to do is the integration through the surface element, which is f dot m ds. Okay, very good. The principal unit normal vector to parameterized surface, if I want to have the principal unit normal vector, I will get the normal vector, and then I will get the unit vector from this normal vector. So, if a parametric surface sigma is the graph of R, which is x, y, and z as functions in u and v, as we did go through it. So, that's the cross multiplication, which is the direction of the normal, as we saw also in the previous slides. So, at a point on the surface, then the principal unit vector, it's gonna be the value of this normal vector divided by its magnitude. And this is generally how we change any vector into a unit vector. So, the concept smooth goes together, nothing, just straightforward. So, once more, as I told you, this is the R controlling the surface, differentiating with respect to its components, U and V. Then making this cross multiplication, we will be able to get the normal vector of this surface. Then dividing on its magnitude, we will get its unit vector through. So, flows across parametric surfaces. A regular surface sigma is said to be parameterized by R, which is U and V, as you can see. Is positively oriented if its orientation is defined by the vector. So its orientation is with the normal vector of this surface, which is, as I told you, as we explained just previously. So making this multiplication both together, this is n dot partial r partial u, this definition or the magnitude. I want you to memorize that F, once you multiply the dot product of NU and V times the magnitude, okay, of DU and V, those two guys will, or this magnitude of the normal vector of the cross multiplication will cancel the magnitude also in the principal normal vector, and we will remain with just only multiplying the value of the function at R times the cross multiplication of the derivatives directly. We don't have to divide or normalize, because once you multiply them together, this is going to be the end. So once more, this is how we determine the flow of a vector field through a surface up to here. And this guy here can be parameterized by this relation. Remember, this for the ds element, or these two elements which determine the flow, okay, which assign the flow of a vector field through a surface, and ds by itself, it's equal to these two guys. So multiplying them together will make this part to cancel the magnitudes on n, and we will end up having directly the relation that we have here for the evaluation. This is why I repeated this part once more, as I want it to be clear with you. And we will take examples shortly, inshallah. Of course, for the negative direction, if this is the positive direction, going upward from on the surface, based on finding RU and RV, making the cross multiplication, giving the normal vector. Also, the negative direction will be the negative of this relation. That's what's stated in here. It's going to be the negative of the multiplication between the vector field and the components of the normal vector after getting its cross multiplication. Okay, let's take this example, which will show you how to go through the details of the flux, or evaluating the flux through certain surface. So consider the surface. The surface here is sigma, given by z, which is 9 minus 3x squared minus y squared, and z greater than or equal to 3. Of course, if you remember the first part of our course before the first midterm, we spoke a lot about parameterizing shapes, how can we find it, how to parameterize it, and this is going to be a great help just to go through it before we continue. It will make you imagine certainly what's the type of this shape. Can you remember what's the type of this shape? Yes, you are right. It's a paraboloid, and it's looking downward, as you would see. He wants you with the normal directed upward, so the normal vector is positive. Determine the flow of the vector field phi. That's the function that we need to evaluate. It's a flux, or the vector field for phi, which is given by the two components, the I component equal to 0. This is y squared in the direction of j, plus 1 minus 2yz in the direction z in the direction of k, across the surface row. So to compute the flow of the vector field, which is the flux, عشان اقدر احسب ده, or in order to evaluate this, I will need to determine. This is mainly the function phi, which is the function of the vector field. يبقى انا بحدد الفيكتور فيلد، حددته اللي هو given y squared. Now I will talk about the surface. هتكلم بقى على ايه؟ على السيرفيس او الشكل اللي انت هتتكلم عنه، او اللي بيتم عليه عمليه انك عايز تحسب الفلو of this vector field on. عايز تحسب تشوف الفلو بتاع الفيكتور فيلد ده على السطح. Okay, really very simple. Across the surface is given by, as I told you, 9 minus 3x squared minus 3y squared, which is represented by the paraboloid. Here we go. That's a paraboloid, elliptic paraboloid. Now it's a circular paraboloid, and with a 9 to the negative direction. That's the vertex, and within the negative direction. And above, z is greater than or equal to 3, so we did the part other than z equal to or 3. So we are actually trying to evaluate the flow of the vector field around this part in particular. This is the plus when you memorize or you go through first the parameterization or the curve, the various curves equations and the parameterization types. Okay, with the normal vector directed upward, so the surface area element, now I will have to determine the surface area element, which is from here, z gonna be the f of z as a function x or y, which is 3 minus x squared minus 3y squared, from which I can get the partial derivatives, and I will consider here, yes, you are right, I can consider here z as a function in x and y, and x and y are like the u and v exactly. So the flux is phi dot m with respect to the s. Now I will need to find r, that's for the surface z. The upward normal vector class, we already know it's going to be the n vector, and I will show you how to grab it. But first, this is the function that we are talking about. In order to get the normal vector on the surface, which is z equal f of x, y, on this guy, in order to be able to evaluate the normal vector through this through this surface, you will have to put this equation equal to 0. I would prefer or recommend having z plus 3 over x squared plus 3y squared minus 9 equal to 0. That's the function that I'm going to get its gradient vector, and the components will be the normal vector. So step by step, here we go. That's z, 3x squared, 3y squared equal to 9. These are the components that are going to differentiate in order to get the normal vector. So that's the gradient of f, as I told you. Differentiating with respect to x, you will have 6 of x. Differentiating with respect to y, you will have 6 of y. Differentiating with respect to z, so you will have z equal to 1. And that's the normal vector that we need now in order to be able to do the multiplication as you would see. I will just clear all of this because we will go, as I told you, step by step. Now I have the normal vector, which is very, very simple. So now I can evaluate the flux, which is phi dot n. See how it connects together. The integrand is f dot n. So all I have to do is to multiply the various components of the phi function. Of course, this is plus, and I and 0. So 0 will be multiplied by 6 of x. Then I will have y squared times 6 of y. Then I will have 1 minus 2yz times y. And this is what's going to happen. So y squared is going to be multiplied by 6 squared. As I told you, the I component is 0, so it will be cancelled. Then plus the last component, the k component, which is 1 minus 2yz. As you can see, I will take this guy and multiply it by 1. So actually, phi dot n ds is going to be 6y cubed plus 1 minus 2yz once you do this multiplication. Once more, I don't want you to lose attention here. It's very, very simple. All I have to do is to multiply y squared times 6 of y. This is 6y cubed. Then 1 minus 2yz times 1. And here's the guy in front of you. Of course, we are integrating. Now we are moving from the surface element into the plane element, dx, dy, or the double integration. Someone would say to me, hey, stop, there is z. Okay, I know the z value with respect to x and y. From here, I can replace z by 9 minus 3x squared minus 3y squared, as you will see down the road. Okay, set up the domain. The domain is already set. We have z 9 minus 3x squared minus 3y squared. And we need to evaluate above z equal to 3. So I will put it greater than or equal to c. And this is will end up the story with a contour, flat contour, which is the function, as I told you, or the part, this is the boundary, okay, of the intersection between our paraboloid and this plane. So it's very, very simple to grab. All I have to do is to replace z by the equation of that plane, as you can see, greater than or equal to 3. Moving on to the other side, it's going to be a negative of 6. dividing by negative 3, so you will have this equation, which is a disk less than or equal to 2, as you can see, and the radius will be root 2. In order to handle this disk, now it's a good idea just to move into polar coordinates as we did exactly in the previous session, in the previous example, I'm sorry. So replacing x by r cosine theta, or r sine theta, and of course dx dy is going to be changed from r d theta. R runs from 0 to root 2 and theta from 0 up to 2 pi. So it's really going to be really very simple. I will have to do this. So here's our polar coordinates. The z function is known now, minus 3r squared after we change. Dx dy will be changed by r d theta. So that's the flux, that's the surface element. We are going to use to change it by dx dy. So now I'm making, instead of integration through the surface, I'm going to integration through the flat area. So that's the domain of dx dy, which is x squared plus y squared less than or equal to 2 for this disk. And so if we make the replacement, we will have this equation. Of course, the replacement will be really very simple, because all I have to do now is just replacing every component. So step by step, if you want to go through it, I will change y with r and sine theta, replacing y r sine theta, as you can see. And for the z component, I can replace it with 3, the value of 3, which is the component of the normal, the component of the plan that we are intersecting with, z greater than or equal to 3. And replacing dxy by r d theta and expanding, we will have this relation in front of us. Here we go. This is 6 of r squared. This sine theta plus sine 3 theta, and so on. Complete the double integration. It's really very simple. All I have to do is to integrate with respect to r, and this is durable because you will have here r squared and the r cubed, making the substitution from 0 to root 2. And then I will integrate with respect to theta in the other direction. I will get the flux, which is 2 pi. I want you to perform this double integration. It's very, very simple. All I have to do is just to start integrating each part. It's very, very simple. Okay, now let's remember the gradient in 2 or 3 dimensions. Once more, I need you to go through this integration. Tell me about it. The r direction is very, very simple. I want you to think about the integration in theta direction, which is also going to be very, very simple, but just with a little bit of the trigonometry. I thought just to give you this hint. Okay, now let us remember this slide before continuing to Stokes' theorem. Before we go further, we saw here how to change the surface integration of certain vector field through a surface into the double integration relation that we already get, how we changed the surface integration into double integration by this hacks, as you can see. Now, I want you to remember that the gradient vector is partial x, partial y in 2 dimensions. All of this was stated in the previous lecture. And you know also that nabla is the gradient vector. In 3D, it will be the derivative with respect to x, y, and z. So this is the definition of a divergence, and we will need it. So I thought just to review it with you, the divergence of a vector field is just simply making derivatives of f1, f2 with respect to its component. So finding the partial derivative of f with respect to x, the second component with respect to y, as you can see. If we are in 3D, we will get the derivative of f1 with respect to x, f2 with respect to y, f3 with respect to z, as you can see here. So that's the definition of the divergence. We already have it in the previous session. Now to the rotation of a vector field, or the curl, if you remember, we already spoke about this. This is the curl of a certain vector field, or the rot of rotation of a vector field, which is really also very simple. This is the f function in 2 dimension. So if I need to find the root of f function in 2 dimensions, very, very simple. It's like the Green's theory. So I'm going to get f2 with respect to x, partial derivatives, minus f1 with respect to y, and this is gonna be the value of the rotation with respect to in 2 dimension. In 3 dimension, all I have to do is, this is the function or the vector fields defined. The function field of a vector field is defined, and the root will be simply in the cross multiplication of nabla times f. So all I have to do, as I told you, I want you to remember my words. All I have to do is to write I, j, k. These are partial x, the derivative with respect to y, the derivative with respect to z, for the components of the vector field f1, f2, and f3, and the making expansion for this guy here, and these are the component the various components. As I told you, don't look at this, but just only directly get the curve of the vector field, and you are done. Okay, perfect. I want you, we will go through these slides, which determine the positive direction if you are moving through the boundary, as an introduction for Stokes. So, if this is the surface, if that's the surface that we are talking about, so this is the surface, and that's the normal vector, and I want to move through the boundary. So instead of dealing with an integration, this is why we are taking this, an integration on the surface, I can do the integration on the boundary. So instead of going through the hustle of surface integration, I can do simply an integration on a closed path line integration for the boundary. It's very simple to determine the positive direction. The positive direction is exactly like we did in the simple closed curves, is to move around the boundary. I will move around the boundaries. I will move here, as you can see, that's the boundary of this surface integration. I will be moving in this direction, as you can see, with my left arm inside or toward the surface. So if you remark here, or if you see here we go, that's a beautiful lady, is moving on the boundary, and her left arm is inside the region. So if I'm moving and my left arm inside the region, that's the positive direction, as I told you. So once more, F sigma is the surface, and the C is the edge or the boundary. There are 2 possible relationships between the orientation of sigma and the contour, which is the C curve. Here we go. That's the contour, the boundary. Here's the boundary. I'm moving on the boundary. Okay? And of course, this part, it's not a flip, but this is the part which is in the opposite direction. So the positive direction of C establishes the right-hand relationship. If the fingers of the right, he's talking about the right-hand relationship, but I myself would prefer this case if a person is walking in the positive direction on the contour relative to sigma, his left arm will be inside. And of course, if you are moving on the other direction, so this is how it goes if you are moving with this direction. But if you move to the opposite direction, you will be walking in the negative direction. Here we go. In the negative direction of the closed curve. This is how it moves. So it's the negative direction. We spoke about determining the positive directions here, and the difference between the contour, the boundary, and the surface integration. And we determined the positive direction of the contour of the boundary in this positive direction and the negative direction. All of this because of this guy, which is This is really very important and very nice too, which is the Stokes theorem, which is here. Now, instead of integrating through the surface, I can replace it by simply getting the vector field dot the dr, or the derivative of the r vector that controls the boundary of the service. And now I will be able to integrate, instead of double integration, I will be integrating on the boundary or the closed boundary. This is really very nice theory, as you will see. Here he is asking you, or for this example, let's go through step by step. Consider the vector field F, which is given by minus yzi, xzj, and xy and k. Okay, that's the components of the vector field. Let sigma be the part of the equation service, which is z equal to the root of 4 minus x squared plus y squared. If you give it a good look, you will understand that's a part of a sphere. Because if you just square both sides, you will have z squared equal 4 minus this guy. So moving it to the other side, you will have a sphere with radius equal to 4. That's inside the cylinder. Okay, so I will need to evaluate the vector field, the flow of the vector field actually, okay, of this sphere which lies inside the cylinder x squared plus y squared equal to 1. Okay, that's the points of sigma, check x squared plus y squared equal to 1, oriented by upward, and the direction is upward, using Stokes theorem. So instead of going through this surface integration, we will be able to do it with the contour. First step is to know, to determine exactly your vector field, which is the function negative yz plus x and z, j and x and y, and the surface, which is, first of all, a cylinder, x squared plus y squared less than or equal to 1, so it's a closed cylinder, and intersected with the sphere of 4 centimeters. So I believe I draw it here for you. That's the shape of the sphere. If you can see, that's the sphere as the x, y, and z, and with radius equal to 4. And that's the cylinder inside the sphere. And I will need to determine the flow of this vector field through this part. So it's very simple, and the orientation is upward, as you can see. So that means I will do the surface integration, okay, using Stokes theory, which means I will, instead of evaluating with the surface integration, I will do or cure this integration on the contour of this intersection, as you will see, or the contour of this surface. So that's mainly what's written here. Of course, you know that the rot of F, it's the cross multiplication of the nabla and the vector field. Okay, very good. I will do it step by step. So that's mainly what's stated about the deviation of the rot F dot N. If this guy happens, if I have the curve of F and I'm integrating on the surface in order to determine the flux, I can change it by the boundary integration, as you would see. Okay, so instead of computing a surface integral of the curve, we compute a line integral of F along the boundary C. Now to the journey of determining boundary C. The boundary of the surface, sigma, lies on the circle x squared y squared equal to 1. Because as you can see, that's the sphere and that's the circle. The intersection between them, it will be x squared plus y squared equal to 1. And since z is equal 4 minus x squared plus y squared, if I replace x squared y squared by 1, I will be able to find the value of z at the intersection point with the boundary. So 4 minus 1 is going to be a root of 3. That's the value of z. So the boundary curve is a circle of radius 1 in the plane z equal to 3. Now I can write r of t, which is, as I told you, the boundary of this relation controlling the x and y and z. Since we are talking about a circle, it will be a very good idea to change to polar coordinates. So it's a r cosine theta, r sine theta, and root 3 for the z value. But here I'm talking about a unit circle, where r equal to 1. This is why instead of doing r vector, which is r cosine t, r sine t or theta or whatever, and then that's the z component, r is going to be equal to 1 and the z will be root 3, as you can see. Of course, we are integrating for the whole circle, so we are integrating from 0 up to 2 pi. And that's the circle that we are talking about, if you can see this one. I'm sorry that I made them very small lectures of the sphere and the cylinder inside the sphere, but because I want you to go through the steps. So once more, I've determined the boundary, which is x squared plus y squared equal to 1, and that's for the z equal to the root of 4 minus x squared plus y squared. Once more, I will need r dash in order to evaluate the contour integral, dr. So it's very simple. I will have to differentiate. Cosine t is going to be negative sine t, sine t is going to be cosine t, and root 3, the derivative is going to be 0. Now I have r dash, and also I have the f, which is minus y and z, x, z, and the plus x and y. Now I will get the substitution, or making the substitution using the polar coordinate, changing everything into polar. So now if I have an x, I will change it by cos t, every y will be changed by sine t, and the hz will be by root 3. So mainly the y is going to be minus sine t times z, which is root 3, and so on. This is why after we make this substitution, that's the value that we are talking about. This is negative sine t, and the z is root 3, as you can see in the direction of I. That's the value of x, which is cosine t, times z, which is root 3. X and y, but for both of them, it's going to be cosine t, sine t. Now, I have f of the r vector components. Now, I will make the multiplication of r dot f together, component by component. So, I will have sine square t, and this is root 3. Then plus cosine over t times cosine t, so I would have cosine square t root 3. And then for this guy, which is cosine t sine t, it will be times 0, so they will cancel each other, it will be cancelled. Now taking root 3 as a common, I will have root 3, which is going to be root 3 times cosine square t plus sine square t, so it will be cancelled, equal to 1. So this multiplication, or the integrand, will be directly root 3. And that's what you will see right now. Okay, once more. Here we go. I will do the multiplication. This is just shaving up stuff and making it suitable for the dot multiplication. I'm getting, this is the integrand, and I will integrate on the curve. That's gonna be just a circle moving around from, as you can see, t from 0 up to 2 pi, since r is constant. So this is gonna be f dot dr. So integrating from 0 to 2 pi of root 3 dt, you will end up having 2 pi root 3, as you can see. I did more examples. I thought to give you more examples on this part, just to make it easy. So now remark that we have the surface integration. Now thanks to Stokes theory, we don't have to go through the surface integration. We can change it and to go to the contour integration around the surface. Okay, once more, here's use Stokes theorem to evaluate. Instead of evaluating the curve or the movement of this function through the surface, and f is given by, this is the vector field, y, z, and x, and it is the upper hemisphere of the sphere, x squared, y squared, z squared equal to 1. Z is greater than or equal to 0, which is the hemisphere exactly. Okay, oriented upward, so it's a hemispherical cap. It's something like this. It's very, very simple. That's if this is V, that's X and Y and Z. So here's the sphere, and that's the plane of Z equal to 0. So we are talking about the hemisphere exactly in the 3 dimension. So that's the vector field, Y, Z, and X. I will have to go now for the surface, which is simply a hemisphere, X squared, Y squared plus Z squared equal to 1, and Z is greater than or equal to 0. So this circle will happen when Z is equal to 0. Replacing this guy here, that means that your boundary is going to be X squared plus Y squared equal to 1, which is a unit circle. That's instead of dealing with the surface integration, I will go through the boundary. As I told you, the boundary will be just only a unit circle with Z equal to 0. So R, it's going to be cosine T, sine T, and 0, as you would see. So the boundary is going to be cosine T, sine T, and 0. Here is R cosine T, but it's a unit circle, so R is equal to 1. And Z is equal to 0 because you are talking about the by 1 plan, as you can see. T runs from 0 to 2 pi in order to get the evaluation of the boundary, and we are in the positive direction. As if you remark, if I'm walking around the boundary of the circle, my left arm will be inside it exactly. So F is sine T. I will start to make the replacement, getting F as a function in R. So Y, as you can see from here, it's a Y is a sine T. Then I will have Z, which is 0. Then finally X, which is cosine T. So it's a sine T 0 equation. Then I have F, I got R dash. I will make the multiplication and integrate through the boundary. But let's do it. Negative sine T times sine T is going to be a negative of a sine